Hi, it's your boy Mr. Tsebe, and today we'll be proving a binomial theorem using mathematical induction. Without any further ado, let's get into the content. So, suppose that you are given an expression like this. Suppose that you are given an expression like this to the power n. This can be written as summation of n r from 0, which is n combination r multiplied by n minus r y r, according to our binomial formula, and then whereby n and r are element of natural numbers and x and y are element of real numbers. So this can be expanded, x plus y n. This can be expanded in this fashion: n 0 times x n minus r, n minus 0, and then y to the power 0, which is just the same as xn. So we can add n combination 1, which will be the same as xn minus 1 times y1. So when we continue adding like that, I'm going to be having n minus 1 times x n minus 1 times y to the power 1. But this is the same as n minus 1 is the same as just 1. So my x here will be 1 and my y will also be 1 plus this will be n, and we have reached n right now. We have added until we reach n. So this will be x to the power 0, y to the power n. Why x to the power 0? Because of when we are going this side, x is losing a power of 1, but y is gaining a power of 1. So if here it was 1, and then we are going to subtract 1, we are going to get 0 here. This is why we are saying x is 1. So we can prove by mathematical induction. This is the where we start proving after expanding this. So we can say that p of n equals to 1. We can just assume that p of k equals to 1, and then we are going to use this part to check if it's true. So it will be x plus y to the power 1, and then this will be the summation of n equals to 1. R, it starts from 0, 1 combination r times x, 1 minus r times y, just r. This can be written as 1 combination 0. It starts from 0. 1 combination 0 multiplied by x, 1 minus 0, which is just 1. And then my y is 0 plus 1 combination 1 times x to the power 1 minus 1 and y to the power 1. This is the same as x plus y, but x plus y is the same as x plus y to the power 1. So this implies that when p equals to 1, our assumption is true. So then when our assumption is true like this, we must formulate our own mathematical hypothesis, which we will call an inductive hypothesis. So we will assume that p of n equals to k is also true. So we are going to be using this notion of x plus y, but wherever we see n, we are going to put k, which is the same as k r equals to 0, k r times x, k minus r times y r. This is what we can do. And then we are going to say that our inductive hypothesis is also true. We are going to assume that it's also true. Then if it's true, that means Pn equals to k plus 1 must also be true. So wherever we see n, we put k plus 1. So even here is going to be x plus y, k plus 1. We are going to say this is true. even here we are going to put k r equals to 0, k r, sorry, it will be k plus 1 here, because of that's where n is. Even here it will be k plus 1. We are using the original equation. And then even here it's going to be k plus 1 minus r times yr. And then we are going to assume that this is also true. So then if this is true, we have to prove it using this part. So we are going to say our LHS is going to be, or left hand side is going to be x plus y, k plus 1. This can be written as x plus y multiplied by k plus, sorry, x plus y to the power k. But x plus y is the same as this part. But what is this part? This part here is the same as this part. Is the same as this part. And this part equals to this thing. So wherever we see this, we are going to put this whole thing. So here is going to be k summation of r is equals to 0, k combination r times x, k minus r times y, r. This is what we are going to put. But it's the same as plus y, k plus 1. So when we are there, so when we are here, actually, this is what we are going to do. We can multiply by x here and then by also y. So it's going to be x plus y, k plus 1 is going to be x, the summation of k, r equals to 0, k combination r, x, k minus r, y, yr. And then I'm going to multiply by y also, and then it's going to give me kr0, kr times x, k minus r times yr. This is what I'm going to have when multiplying like that. But we know that a to the power 1 times a to the power 2 is a to the power 1 plus 2, which is a to the power 3. So we are going to multiply this x here, and then it's going to add 1, and then this y here, and then it's also going to add 1. So that's what we're going to do right now. So this will be the same as the summation of kr equals to 0, k combination r, kx, k minus r plus 1, because of we multiplied by x, multiplied by yr plus y, plus the summation of kr equals to 0, k combination r times kx minus r times yr plus 1, because of we multiplied it by 1. So this is what we are going to be having like that. So, but how can we make this exponents and even this one to be the same? This is what we do. So we are going to say the summation of k from r0, k combination r, x, k minus r plus 1 multiplied by yr plus the summation of kr equals to 0, kr. So this is what we're gonna do. So check this thing out. So this will be yr plus 1. So how can we make this to be the same as just yr? We're going to subtract by 1. So if we subtracted by 1, we have to subtract by 1 also here. And then if we subtracted by 1 also here, so this is the same thing that we are going to do even on x. So this one will be it will be k minus r plus 1, because of it will be r minus 1 like this. I've subtracted here because this is my n, So this will be my r. So it's k minus this whole part. It will be there. So this will cancel out this one. So then I'll be left with the summation of k x equals to 0, k combination r times k minus r plus 1 multiplied by yr plus the summation of k r equals to 0. This will be k r minus 1, and then this will be the same as k minus r plus 1. This is what we are going to have, plus multiplied by yr. So we can see that our exponents are the same here. Oh, this is x, and then this is the exponent of x, k minus r plus 1. We can see that the exponents are the same here. So what is it that we are going to do? We are going to say k, the summation of x equals to 0, k combination r multiplied by x, k minus r plus 1 times yr plus k, the summation of k combination r minus 1. I'm just rewriting the whole thing. K minus r plus 1 times yr plus, we are going to add this term here because we want to prove that each and every term is going to be having the power of k plus 1. So it's going to be x plus y, k plus 1. I've added that term there. So, but this term here, let me show you something about this term. So, but then that term there, it can be broken down in such a manner. It can be said that it's k plus 1 plus y, k plus 1, like that. So I can just add this on the summation of x and this one on the summation of y. So which will be the same as k, the summation of, or let me just start by adding it now. K plus 1 plus the summation of k r. R, it will approach 1 this time. Since 1 is added here, it means that our r right now will approach 1. So it will be 1, sorry. So our k r multiplied by x, k minus r plus 1 times yr plus this summation again, the summation of y, which is k. Okay, this r is 0 here, sorry. Even here is not x, it's r. So here is going to be summation of k r equals to 0, k r minus 1 times x, k minus r plus 1 times yr plus I'm adding this term, which is yk plus 1. So I can just erase this part. So, but we can check this part here. We can check this part, the whole of it, and try to factorize it. So we are going to be having x, k plus 1 plus, but we see that k, the summation of r equals to 1, x, k minus r plus 1 times yr is a common factor. So inside you're going to be having k combination r plus k r minus 1 combination multiply plus, because of we already factorized, plus y k plus 1 can be written this way. So since we proved that every term will consist of 1, and then if it consists of 1, then therefore our r will change to 1. We can exclude this because of it's already proven, this one, that every term of binomial will contain this exponent. So we can just exclude it. So when we exclude this, check what happens to the exponent, but it's the same as y k plus 1. But check when we exclude it. So when we exclude it, this is what we have. K r, it goes to 0 because of those exponents are taken out. So it will go to 0, and then this will be the same as combination of k r plus kr minus 1. This is what we are going to have, times xk minus r plus 1 times yr. This is what we are going to have. But using Pascal rule, if you can go and check one of my videos, I made it about Pascal rule, then you will know that the k combination r plus kr minus 1 combination is the same as k plus 1 r combination. Is the same as this part. So wherever I see this, I can substitute this. So then x plus y, k plus 1 will be the same as kr equals to 0. This combination will be the same as k plus 1 r. It will be the same as k plus 1 r multiplied by xk minus r plus 1 multiplied by yr. So I can remove this part, which is just the same as k summation of r equals to 0, k plus 1 r multiplied by xk minus r plus 1 times y r. Hence, this is proven by mathematical induction. So it means that wherever Pn equals to k plus 1 is a biconditional statement of P of n equals to k, when P of n equals to 1. Therefore, this is mathematically inductionally true. So guys, please subscribe and also share with your mates.